more introduction, you should probably know him by now. But Laurent has many works, including in shape analysis, in geometry, but also in statistics and machine learning. So I believe this talk is will give us a nice sort of blend of these different topics for diffeomorphic learning.
Yeah, for those of you, so that's a very new student, but those of you that have been here a while, you probably noticed that every time I come here, I give the same talk, while trying to make every effort to make it look different than the previous one. And well, this is not you today. It's the same. It's going to be the same talk as the last 10 times I've been here, but it will look different. So just bear with me. So a bit of motivation, and because it's the first seminar. I'm very glad to have that many people in the room. It's the first seminar of the year, which means that every student is worried that they will not be able to fulfill their 10 courses requirement in the seminar, and everybody comes here. And so I'm very glad that I volunteered for this early seminar, especially that last week we didn't have a seminar, so it's even more pressure. So a bit of motivation. So you can think of neural networks are a way to try to compute some very complex transformation of an input data and apply some classification rules at the end. And every reasonable intuition grounded in statistics told us that that was clearly possible, that it would work, and it did work. So my motivation here is that, well, if this kind of approach works, why not try to use the only thing that I know how to use, which are how to estimate diffeomorphic transformation in large dimensions, and the proof that I know is that I wrote a book about that. So that probably, sure, if you do that, you have to know about it. And so the idea is just see what happens if we force these transformations to be diffeomorphisms. And so let's first try to describe how this can work, and then see what at least some preliminary results provide. So, and the last line is important because it just relates to where that comes from, explains why this talk is exactly the same one as the one I gave before, and the one I gave before. So, the use, people have been using diffeomorphism. People, especially people in this university, have been using diffeomorphism as a tool to perform shape analysis for a long time now. It could be more than 20 years. And diffeomorphic transformation is actually a powerful tool to analyze shape, because it's probably a very natural way to move from one shape to another. There has been a few applications to machine learning, two that I know of. So one in 2009, which is probably the closest to what I'm going to propose, which was called diffeomorphic dimensionality reduction. And so what was written by Warner and Scholkopf, and one which is a more linear approach, a linearized approach, introduced by Trouvé and Yu in 2001. So here's the model, which is quite simple. The predictors will take input data, X, that I would assume to be d-dimensional, and transform them in a diffeomorphic way, and then apply linear classification. So formally, it just takes this form. There will be a parameter at the end to characterize final classification rule, and there will be more parameters to describe the diffeomorphism. And just for those that hear this for the first time, the diffeomorphism is a one-to-one transformation, which is C1 and has C1 inverse. So more notation. We're going to assume standard training set when you have examples and classes. So the data, the examples are denoted X, and the classes are denoted Y. And so we assume that Y belongs to a finite set, which is called C here. If you have a training set, you can, and you have a diffeomorphism, you can transform it by simply applying a transformation to every one of the X's. And the approach will simply minimize this objective function. Spend some time describing how this can be done. So the first term is this function gamma, which is a standard loss function or function that is minimized for linear classifiers. And I gave an example here with logistic regression, which is what is used in this these experiments. And there's a penalty on the parameter of the linear classifier. Here, just using an L2 norm. And then this classifier is applied to learn using the transform training set. So after transformation by diffeomorphism. And this diffeomorphism is controlled in terms of its essentially regularity, its smoothness, by how far it deviates from doing nothing, how far it deviates from the identity. So this is an objective function. Essentially, it's the classification function plus some regularity penalties. So it's basic penalized learning, except that this is a rather unusual penalty here because this will be defined as a Riemannian distance in the diffeomorphism. Just to give to show you this example once, what we compute here is, so you take f of z and theta for a given class to be this logistic probability, and you do maximum likelihood on the transform data. So the z here would become x transformed by the diffeomorphism. So that is the framework, and so I need to describe, and I may have to spend a little time on that, to describe what how you build distances on diffeomorphism group. So we are going to first build diffeomorphisms as solutions of ordinary differential equations. And to define these ordinary differential equations, we have to define the flow, I mean the equation itself, which will take that form. And so we will have to define this time-dependent vector field V that describe how points are moving over time. So we will put these V's in an appropriate space, and the appropriate space is this Hilbert space capital V, which is a space of vector field, which are smooth enough. And from a function space terminology, what we assume is that the space is continuously embedded into a space of P times differentiable function, P typically being 2 or 3, depending on what you need to prove theorems. The embedding so ensures that the vector fields are smooth, and the Hilbert assumption ensures that we have an inner product which makes every computation easier. Actually, it ensures that the Hilbert space is what is called a reproducing kernel Hilbert space, which is, I mean, some of you may have heard of reproducing kernel Hilbert space in the case of support vector machines. The only difference with support vector machines, for example, here is the fact that you are working with spaces of vector fields or spaces of functions, so the kernel is matrix valued. But what is important is that you have a function that takes 2 points in RD and returns a matrix with real coefficients, such that when you fix one of the 2 points, fix y, and you apply this to some fixed vector little a, so this expression now becomes a vector field as a function of x in RD, and this vector field belongs to the space capital V. That's the first requirement. And the second requirement is this identity, which say that if you take this function, this vector field, and you compute the dot product with any other vector field in capital V, then you have an evaluation function. So this is the definition and the characteristic properties of a reproducing kernel. And the good thing is that, well, our assumption imply that V has one kernel, but even better, you don't need to, I mean, you can, there's a whole family of kernels that you can use and that you know correspond to some space V without having to make V explicit. So that's the approach that we use. We assume that we have a good reproducing kernel.
Question. Do they depend on the inner product? The kernels?
Yes, I should be denoting it K sub V, and it really depends on the Hilbert structure. So returning to this slide, we will consider this ordinary differential equation that for V that satisfies these properties, for vector time-dependent vector field that satisfies these properties. And by the way, I'm using, if I hope it doesn't bother you too much, but I'm using V of t when V is considered as an element of capital V, so vector field that depend on time. But when I want to explicit the value of this vector field as a, by the way, I mean, I've been teaching all semester in that room. This marker was just a nightmare. The lifespan is 5 minutes. So this one is still alive. So V of t y is just what I could also have, you know, the V of t. So, and I'm teaching after Jim Field, so I just imagine how, in what poor shape the markers are after. So, where was I? So yes. So now you take this differential equation. You take this differential equation here, and you study it at some point x at time t equals 0, and you follow it over. You need, say, time t until time t equals 1. You get a new point. You call it phi of x, and you can do it for each x. And the basic theory of differential equation tells you that phi is a diffeomorphism. So that's how we concretely build diffeomorphisms. And when you do that, you can build the whole family of diffeomorphisms. This family forms a group. And I'm not going to use this notation, but that nice notation with this group. And on this group, you can define a distance, which is just how much you have to pay by moving points, to move points, and as measured by this expression, to go from the identity to some diffeomorphism field. So this is the whole framework, and this defines, so this cost function, if you take phi1 equals the identity, is just this lambda function that I defined here. So this distance is this lambda function. Square root, because we want to be a distance, and that is measured as the minimum norm for any v that depends on time that can build this diffeomorphism. So at the end of the day, you have a way to rewrite the objective function of the problem as so the same two terms that we had before, which is so the classification part, the penalty on theta, and this term now that replaces the distance, that is essentially lifting the distance to the space of time-dependent vector fields, and so you need to explicit how phi depends on v, and this is by the fact that phi satisfies this differential equation. And there's a bunch of theory that prove the well-posedness of this kind of problems.
So your tangent space is a Hilbert space here, is that right?
The tangent space to
your because you've got a Riemannian metric, so you've got some.
Okay, okay, all right. This is infinite dimension, so
yeah.
Riemannian has to be taken with some care.
Yeah.
Although in some cases it's actually a Riemannian metric. But you can think of the tangent space to the identity to it's in general it's not a nice manifold. So you can define a Riemannian metric or a short of next metric using this, but the nice manifold, for example, would be the diffeomorphism that are p times differentiable and with some supremum known. That defines the Banach manifold with a constraint. So then on that you define this metric, which is stronger than what I mean. Some elements in this space do not have a finite norm for this metric, sorry, weaker than that. But and then you can define.
So this V is not related to the tangent space.
V is for vector field. The notation V holds for vector field,
okay.
not for tangent
I mean,
vector.
your Hilbert space from your reproducing kernel Hilbert space, that's not related to the tangent space.
If you want to think, okay, I mean, in say loose terms, this is the Lie algebra of the diffeomorphic.
I see.
Up to a lot of stretches.
Okay. Thank you.
So there is a trick that, of course, we're also using in shape analysis that allows to reduce the dimension of the problem to something that is comparable to the size of the training set. And just how that works. Because at the end, your objective function only depends on what. Oh, it's the other way around I wanted to go. Your objective function will only depend on what will happen on the training data. Phi of 1 applied to T0 being the deformation of the training data. You only care in the whole problem on the trajectory that the training data will have, and so you can optimize with respect to, you can fix this trajectory and optimize with everything else, and when you do that, you find that the optimal V has to take this form, which is now a form that depends on some unknown parameters, this AK of T, and on the trajectories, and on the curve of the space. And so this leads to a reduced problem that can be written in this form. So same form, there's a plus missing here. Same form as before for the last part, but the norm of V becomes something that takes this form, and so it's finite dimensional here. So the only place in which you have an infinite dimensional term is with respect to the time parameter that needs to be discretized for implementation. So, and as written here, what you end, at least for if you fix it, what you end up with is an optimal control point. It was an optimal control point already before. So for all of you who took Nicolas' course on optimal control, you know already that the next slide is going to be on the contrarian maximum principle. No? Oh yes. So the to characterize the solution of this problem, the simplest way is to use the contrarian maximum principle that essentially works like that. You define a Hamiltonian. In that special case, it takes this form. So you define this function that it depends on the points that are moved, it depends on the control, which is in that case A, all these vectors A. And it depends on a new variable that is called the co-state, and that has the same dimension as the vectors that are moved, which are called the state. And once you have that, you can have necessary conditions for the optimum, which is just written in that form. These are the usual Hamiltonian equation for a Hamiltonian system when you fix A. And in addition to that, A has to satisfy this maximum principle, which say that the Hamiltonian is maximal at the optimal value of A. And you have some boundary conditions. So that just characterizes the minimizer, and it does more than that. It essentially describes the gradient of the objective function with respect to these parameters. So I'm forgetting about theta here, because theta was simple. It's a logistic regression is easy to deal with. So with respect to these parameters A, the differential of the objective function is given by this system of equations. I won't talk much about them. It's just that this is, well, maybe I should. No, let me do it when it's discrete. So it's a system of equations that can be solved. If you're given an A, you get computation of the gradient given by the expression which is provided here. And if you're in discrete time, so the only thing that changed here is that you have a sum instead of an integral, you have essentially the same approach, and the algorithm that computes the gradient is essentially computing the solution. I mean, taking the current value A of your that you're trying to optimize, and generating the trajectories of the points, which are called Z, and from this trajectory doing back propagation, dynamic programming, and computing the vector P, and the gradient should have been written somewhere, which is, oh yeah, it's U, which is given by this expression. So it's essentially dynamic programming or back propagation that is used in this approach. All right, a few points that need to specify before I move to examples. So first you need to choose your reproducing kernel Hilbert space, which for us is choosing a good reproducing kernel. And so here are some examples. They always come with some scale parameter, and I may come back to it in a moment. But in the experiments I will show, I took this kernel with scale equals 3. So once you have this kappa, remember that k is matrix value, so k is kappa times the identity in that case. When you have this kappa, you have everything you need to program the algorithm, except a few details, which are how you choose the parameter lambda, rho, and sigma in the objective function. Rho is coming in the definition of the kernel. Question. So I want to skip that one. Yes.
Is time discretized uniformly?
In my implementation, yes. It doesn't have to be, but it's much simpler. Okay, you can do a little more than this kernel, reproducing kernel Hilbert space by just adding the possibility of doing an affine transformation also while you're moving according to the vector fields in this kernel, so that adds new variables to the problem that are represented by time-dependent linear transformation and translations that modify the evolution of the trajectory. So before we didn't have these two terms, we just had that, and now we have that comes in addition, which allows to have more freedom in in the motion, and you just have to change the objective function and add a penalty, for example, something like that, for the affine transformation. So this will be used also in the algorithm. I just want to mention that we're not deforming shapes. I told you that I would try everything I could to make it different from the previous talks. So, but we're actually not deforming shapes. So if you think of the approach which is called deformable templates in, for example, pattern recognition, the idea is to use a transformation, diffeomorphic transformation, that deforms a template and matches it to some target, something in the image. And so here also you try to estimate something that looks like a diffeomorphism. And I just want to mention that this is infinitely simpler than what we're trying to do here. This deformable template approach is essentially dating act the diffeomorphism on the right of the object we're interested in. And so you have an image, you let a 2 by 2, a diffeomorphism R2, for example, apply to it, you have a deformed image. It still looks like a little like your original image, just the shape. If the diffeomorphism that we are talking about here are all possible transformation in the image space. So if you are dealing with n by n images in the n square dimensional space, and I did experiment with n by n with for n equals 14, otherwise my code crashes. But anyway, that's the transformation that are allowed, for example, could scramble all the pixels of the image, just make it completely impossible to interpret, and that would be okay as something that belongs to the group of diffeomorphisms. So this slide is just saying that what we're trying to model is a very wide object in terms of the transformation that can apply to the data. So it's wild, but maybe it's not enough. It's definitely not enough. If you look at this example, a very simple example in 3D, so you have two, I don't know if it's easy to interpret from the image, it's just something, just two toruses that are rings that are crossing each other, so that if you apply a diffeomorphic transformation of the data, then there's no way you'll be able to separate them. And just, this is, oh, by the way, just a warning, I had a lot of problems with my videos before, so let's see. Yes! That's what a diffeomorphic transformation can do to separate the data points. So it's trying to make this these two point cloud, the red and the green, separable by a linear transformation, and so we'll probably put the linear transformation somewhere here. And of course, still making a lot of mistakes. But what you can do, which is a kind of cheap trick, is, well, you're already working in high dimensions, so who cares, add one. And if you add one dimension, then you allow to the transformation to have more degrees of freedom and stick out of your restricted space for which there was no possible diffeomorphic transformation, and allow for full separation. So here, now we are working in 4 dimensions, which I cannot show you exactly. So we are going to show you it. I mean, it's projecting in 2 dimensions, and then on 3 dimension, and then in 2 dimensions because we're looking at it. So the way, and every time we'll be having large dimensional example, the way the projection is worked out is that so you're doing logistic regression. So you use, for example, if you have 2 classes, you have one direction that represents the discriminative direction, and then you have 2 more to find, and so the 2 additional directions are computed by principal component or singular value decomposition on the space perpendicular to the discriminative direction. So just trying to find the best representation to visualize the space, knowing that it's going to be.
So how do you know that 1 dimension extra is enough?
was in the experiment. You can, I mean, if you have 2 classes, 1 is enough. You can prove that. If you have n classes, then you need n minus 1. But even with n classes, 1 has been enough in the experiment. So yeah, that works also. And so that is going to be, if it's the right thing, it's going to be to look a little magical. I hope it will. No, that's not the right one. Oh, it's the same one. So, oh yeah, it's all that I said, and what I just, that's the answer of your question. So if you have a binary classifier, just 2 dimensions, then you can make up a diffeomorphism that will separate the 2 if you have access to an additional dimension. So this is what I wanted to show you. This is actually working in 4 dimensions, but if you look at it in this projection, it looks like it's separating the points. So it does something that is forbidden by a diffeomorphism, but it's actually a diffeomorphism in a higher dimension. Another example for a 2-dimensional data, which shows that adding a dimension can help also because, well, of course this is separable by a diffeomorphism. You can take this point and put it out there and then you get a linear separation, but you can do that also. And I do have a video. I'm living dangerously. Well, I thought, oh no, I did. So that's transformation. Okay, that's what is estimated. So I'm going to present a few examples. I have plenty of time. So first, so we use 10 intervals for the time. I will show some comparison on what happens if you have fewer or more time steps. The implementation, so the optimization was conjugate gradient with the right inner product. I mean, that is well adapted to the group of diffeomorphisms. Essentially, the inner product for V applied to the tangent space. And so with that, it seemed to have been the best. It was actually better than BFGS in that setting. And so I used that. And I tried to run the algorithm, so no early stop until it's done, things are looked at, they are converging. So it is really at least a local minimizer of the objective function that we obtain. There are a few parameters that needed to be set for the model. So one was the scale of the kernel. You remember this rho parameter? It was a long time ago, so let me show it again, this thing. So this is probably the most, this is the next one, are the most important parameters. And so for that one, so you think about it, we're looking at vector field. The vector